Hi everyone, welcome back. So let's try out another group problem and see if we can manage to solve it. So what are we looking at? Well, distributed force. Not quite fun. It'll be okay. We got a rope again, attached to the wall right here. We got a pin connection. No rolling connection or anything over here, just a pin connection and a rope. Seems legit, seems safe. Probably wouldn't hang from it, but if I had to. This could be nice and handy. Now, how are we going to do it? Well, pretty much the same way as last time. What are we trying to find? Well, we're trying to find the internal forces right here at point C, which shouldn't be too terrible. So, let's get to it. So first off, we're going to need the reaction forces. Okay? We're going to need reaction forces. So how are we going to find that? Well, first we actually got to draw a free body diagram. And wait a second, what happened to our point B? Why no reaction force right here at point B? Well, we could have had that, and that would have been completely fine, but it makes a lot more sense just to cut the rope. Cut the rope, and suddenly, wait a second, this looks a lot like our previous problem. What a guess. Second thing is this distributed load. Well, we can go ahead and make it into a point load. How do we do that? Well, we take 150. It's pounds per foot. We multiply it by 12 feet, so 150 times 12. Well, what's that going to be? That's going to be 1,800. And that 1,800, where does it act? It acts halfway across because it's a nice little box shape. Remember, where it acts is the centroid, whatever this shape is for your distributed load. This is a rectangle. Centroid of a rectangle is at its center. If it's a triangle, it'll be different. Okay, so we've got these forces. I'm trying to find the reaction forces right here, and I also need to know the tension. So I've got three unknowns, and luckily for me, I've got three equations of equilibrium, so it should be pretty easy. Now, if it was me, I'm probably going to do some of the forces in the y direction first because I can solve that instantly. So, they always do it in a different direction than I expect them to. Yeah, that's okay. But here you see it, some of the forces in the y. There's only two forces in the y direction. That's the 1,800 pounds going down and the AY going up. So AY is going to be equal to 1,800 pounds. Makes sense? AX, that would require some algebra to do first, so we have to do some moments around a point. And I'm going to do around point A because it gets rid of one of my unknowns. So then I only have two things causing a moment. I have this 1,800 pounds causing a moment in the clockwise direction, and I have this tension, which is causing a moment in the counterclockwise direction. So the tension causes a positive moment, the downward force causes a negative moment. As a note, just completely forget signs for the forces. Like the forces, distances, don't worry about any of the signs for that. Only look at, is it counterclockwise, is it clockwise? When it comes to your moments. That's the important detail. That's what you care about. That's where this sign comes from. It's because it has a clockwise moment, not because the force is going down. There are times where the sign can work, but it gets really wonky really fast if you start focusing on that. So don't. Okay, well we do that. We work on our math. T times 2.5 feet. Why is it 2.5? Because it's 2 from here, and it's another half foot from the center to here. And we only care about the perpendicular distance. This is a horizontal force. That's a perpendicular distance. That's what we need. So tension times 2.5 minus 1,800 times 6. Vertical force, horizontal distance. So we get 4,320. Then we realize that AX and the tension are the only two forces in the x direction. So AX is also 4,320, just in the opposite direction. Now we have our reaction forces, which is nice. We need to cut and figure out what to do at point C. Now, I'm not going to skip to the next page. I'm just going to go ahead and erase a little bit of this stuff so we can actually see what's going on here. I've got a question for you. I'm going to cut right here because that's where I need to find the internal forces. What side should I keep? Should I keep this side or this side? What do you think? In my opinion, we should keep this side. Now, why should we keep that side? Well, one is short and it's simple. This one has a two-dimensional shape. This is a, well, it's one-dimensional shape. It's a flat line. It's technically 2D, but we'll go with that. Also, this AX will not cause any moments on this nice little section. This one gets kind of weird. We have two forces, both of which are going to cause a moment, and it just gets a little bit more difficult. You're having to think about this in two directions. This is a nice straight line. If you can make it a nice straight line, keep it a nice straight line. So, we do that, we cut. We have this little section right here. It's a 3-foot long section. And don't forget, we still have a distributed load. Distributed load doesn't go away. Just we had the 1,800 pounds at that one point. That was our equivalent load. When we cut it, we have a new equivalent load, which is still at the center. And in this case, it would be 3 times 150. So it's 450 pounds. Okay, we already know what our reaction forces are. We have our 450 pounds. And then on that section that we cut, we have our shear force, our normal force, and our moment. Why is it pointing down? Because on the right side it points down. That's just your sign convention. There are good reasons for that. Read your book. It talks about it a lot easier than I can. Okay, and with this we have 3 equations. The first one would probably be the easiest, the sum of forces in the x, because this is in the x, that's in the x, that's it. That's all there is. And so NC will be 4,320. But negative. It's supposed to be going in, so this would actually be in compression, not tension. And does that make sense? It does make sense. It's bending down. This is going to get squished as it bends down. I can deal with that. And there, of course, will be in tension. Makes sense. Then we look at the y direction. We've got 1,800 pounds going up, 450 pounds going down. There's only 2. And so our shear force would be 1,350 pounds. And we drew the right direction, so it's just a positive shear force. And finally, our moment, we take our moment about point C. You can do it anywhere. Just choose what you want. Doing it around point C makes a lot of sense because that's what this moment is. So if we do that, we get rid of all these other forces, or get rid of these 2 forces right here. But we still have a moment caused by the 450 pounds and this 1,800 pounds. This guy, no moment. Why? Because it is going straight through point C. It's the same thing as if you tried to push on the hinges of a door. It won't do anything. Like, if you push on the hinges of the door handle's right here, and you're pushing right here, it's not going to open. That's going to happen there. It's going to look weird. So don't look weird. Push on the side with the handle. That actually causes a moment. A force going straight through where you're trying to turn it doesn't have a torque. It's no distance. Okay, so when we do that, we get 4,725. Be careful with your signs. I'll go ahead and erase a little bit just so we can see that more easily. So from this point, this one goes straight forward and then down. That is counterclockwise. This one goes straight forward and then up. That one is clockwise. So this one's negative, this one's positive. You can choose whatever direction you want it to be positive, but normal sign convention is counterclockwise is positive. So with that, we saw we have our internal force at that particular point, and we're good to go. So hopefully this helped you. I hope you enjoyed this problem, and I'll see you all next time. Bye-bye.